Hello, my name is Dionysis. I'm a postdoctoral researcher on blockchains here at Stanford. And today I will do a short video describing one of our recent papers called Logarithmic Space Mining, which talks about how a miner can produce blocks on a blockchain without actually having to synchronize everything and download the whole blockchain state. So let's switch to the whiteboard. All right, so as you know, the blockchain is a structure that consists of blocks. It looks a bit like that. It has a genesis block, and then it keeps growing, and it has many blocks, and then eventually it reaches the tip where we have some recent blocks here. So in between this period, there could be many blocks. So when node wants to synchronize with the blockchain, what it typically does, if it's a full node, is it looks at all of these blocks, it downloads them, including their headers and their body, and then it downloads also all the transactions in their bodies and verifies that the blockchain checks out. It's a correct blockchain, so it verifies that every transaction is correct. All right. So the issue with that is that the blockchain can grow to be quite large. So the number of blocks here could turn out to be tens of millions over a few years, especially if blocks are generated quite quickly, as is done in Ethereum, or even faster in Harmony. So this chain size, so if we denote by C the chain, this chain size could be quite large. And these full nodes, they have to download data that is proportional to the chain size, so big O of C, in addition to having to download transactions for every block. So one simple solution, the SPV solution that you know about, is that I just download block headers for all the blocks, and then for those blocks that may contain some transaction that I'm interested in, what I do is I retrieve the transaction that I'm interested in, and there's a proof of inclusion of that transaction within my block. So this still has size big O of C, so it's linear in the execution time prior to synchronization, but it requires me to download much less data. So the problem we're trying to solve here is that we have a newly booting client, and this client is just, you can think of it, it could be a new miner that wants to synchronize with the blockchain, but hasn't really downloaded the blockchain yet. And we have some network of people that already hold the correct blockchain. And this newly booting client is connecting to all of these and downloading some data. And it's trying to figure out what is the correct blockchain to mine on, right? So some of these people can be honest, but some of them can also be adversarial, and they could be giving false information. So we call these the provers, and we call this guy the verifier. So this problem typically is more pronounced when this verifier is a mobile wallet and it wants to synchronize quickly. But on this particular paper, we're focusing on the case where a miner is trying to boot to the blockchain and is trying to mine new blocks. So the scheme I will discuss today, we call it log space mining. It's a scheme that works in the proof of work setting, hence the word mining. But actually, we do have a new scheme coming up very soon, which allows for log space verification of transactions in the proof of stake case as well. So that would be log space, let's say, minting of blocks. So this is possible, although today I will focus on the mining as it's a problem that we've already published something on. So the idea with this is that first of all, in every block that you see, if you're a miner and you're following the SPV protocol, you're just downloading the headers for these blocks, so you don't really see transactions. And then at some point, you have downloaded the chain, which has K blocks at the end. And what you've done is just a little bit more precisely. You're here the verifier, right? You've synchronized with the network by talking at multiple provers. So these are your provers. One of them could be honest, some could be adversarial. they sent you some chains of headers, of block headers, and then you decided that this is the chain that you like by basically counting blocks or counting difficulty in the case of proof of work, and getting the longest chain or the chain with the most proof of work, so you know what it is. And the thing is that you just have block headers here, so you don't have really transactions. But what you do is you take the last chunk of blocks, the last k blocks, and for those blocks, what you do is you do download the root of the state tree. So you take the kth block from the end, let's say, in your chain. So let's denote that C of minus k, the kth block from the end. And that block you download fully. You can download all of its transactions and all of its state tree. So if you do have that tree with all the state, not just so in the block, as you know, there's a tree of transactions and a tree of states. You can download both of these. Then if you have the tree of states, then from that point on, let's say that this is the block that we have the state of. If a new transaction arrives in my mempool, I can actually verify it against that state and produce a new tree with some new state. So I don't really need to look at this blue parts state at all, but I still need to download all the headers. And there are various ways to actually optimize even downloading this whole state thing. These are orthogonal papers to ours. They're using some interesting data structures. For example, there's the EDRAX paper. Let me just write it down so that you can look it up. So this is a paper by Babis and Alexander Cheponoy. So yeah, you can look it up. It's a very interesting paper on how to make these things more efficient. But the thing that we are focusing on here is that we're assuming that you can actually update the state efficiently. So either you download the full state and you update it, or you do something more clever. But in our case, what we are focusing on is these block headers, whether you have to download these block headers. And this is the portion of the chain. This is let's call it the C up to the kth block from the end. So this is a long portion of the blockchain, long portion. And what I mean by long portion is that it grows linearly with time, right? So the more that the blockchain executes, the more this portion grows. Okay, so how do we solve that? So the idea is to use a structure called Nipopause for the case of proof of work. This is non-interactive proofs of proof of work. So there's a previous protocol that we developed quite a while ago, maybe it's 4 years ago now, 5 years ago now. So this protocol is a way to synchronize this verifier with the rest of the network without downloading all block headers. So let's do an overview of how it works. I will not go into the details of the security of this protocol, but I hope to give some intuition. So the way this works is you have this chain of many block headers, and you want to synchronize, you want to figure out what is the longest chain when you have received multiple ones. In fact, you want to figure out what is the k suffix of your longest chain without actually downloading all the blocks here. So the simplest thing you could do is you could ask a prover to just hand you over these last k blocks. But that's not sufficient because they could lie to you. They could just say, oh, these are the k blocks that are most recent. They have nice timestamps. They're all recent and so on. But they could have been older. They could be something like a fork on the blockchain that is malicious, or even just blocks that don't even go back to Genesis. So that could be problematic. We want to find the suffix of the chain that contains actually the most proof of work or the longest chain. So the way that we will do that is we will do some sampling of blocks at this area that will represent the proof of work that has gone into this chain. So the way that this will work is that we will look at the hash of every block. And in the case of proof of work, you know already that this satisfies the proof of work equation. So this is the POW equation. What it says is that the hash of the block must be below the mining target, or said differently, the hash of the block must start with a particular number of zeros. But the interesting observation is that some blocks satisfy this equation much better than others. For instance, the hash of the block might start with 1 extra zero, or 2 extra zeros, or 3 extra zeros, or let's generally write a mu extra number of zeros. So that would mean that this is actually a block that starts with mu more zeros than needed for it to be valid. So this block starts with mu more zeros than needed for validity by the target, right? For validity by the target. This is the target. This is the mining target. Okay, so these blocks, we call them super blocks. We call this a super block or a mu super block. So if it has an extra zero, we call it one super block. If it has a 2 extra zero, it's called a 2 super block, and so on. And these are exceedingly rare, as you can imagine. The probability of a block being a super block of level mu, given that it's a valid block, right? This is going to be 1 over 2 to the mu. So if we're looking at, let's say, level 10, let's do one example. So mu is equal to 10 gives us that the probability of B is 10 superblock will be it will be 1 over 2 to the 10. So it's 1 in 1,000. All right, 24. Okay, so you can see this exceedingly rare. So these things, they appear quite rarely within the chain, right? So you have a block that is a super block, let's say a 10 super block, then you have many blocks that are 0 level blocks, then you can maybe have another super block, and then some more 0 level blocks, and so on. So the idea for this synchronization protocol is that instead of actually sending all of these headers, what we do is we create these pointers between those super blocks so that they form their own super chain, right? So they're connected. And this is required so that the verifier is convinced that they have been produced in the correct chronological order. And now the light verifier, the super light verifier, okay, so if SPV is called light, this is called super light. This is a super light verifier. What it receives from the provers in this case is just those samples of blocks, those samples of super blocks, right? With these long lists, long links, right? So this is called an interlink, right? Because it connects blocks that are far away in the chain. And what this verifier does is it checks that these blocks actually are super blocks. It can do that because it can look at the header of these, it can hash them, and then check that the superblock equation is satisfied. So this can be checked here. So checks superblock equation. And this actually is like this equation here, right? This is the superblock equation. Very good. And then if it receives some other alternative chain that also has superblocks of the same level, what it will do is it will just compare their lengths. So we'll just check again that they're valid in accordance to the superblock equation, and then it will compare their lengths. So it will see that maybe this one here has 4 superblocks in length and this one has 5. So by comparing them, it finds this prefix of the chain. So it finds this prefix of the chain. This is what the verifier sees, right? It can assume that in between those, there exists some black blocks, but they're not really shown here. And then towards the end, you have these nice K blocks that you can look at the state, download fully, and start mining upon. So this is the portion where we we do a longest chain again, but we do a longest chain based on the superblock equation. That's the basic idea. That's the gist of it. The actual construction, the actual way that these things are sent over the network is a little bit more complicated. In fact, we need to include multiple levels. So here I've just said that we include some level mu is equal to 10, let's say. But in fact, what we need to do is the closer we get to this boundary point, we need to start including more levels. So we need to go down to level 9. And then as we go further closer to the end, we need to say, okay, I'm also including level 8 blocks and so on until I reach level 0. So you can see that as we get closer to the present, this gets denser. So as we get closer to the present, this becomes denser. That is to say, lower levels of superblocks are included. Okay, and the reason for that is included in our security proofs. It plays an important role in security proofs. If you actually don't do that, the protocol is somewhat broken. But if you are more interested, there's a few papers around this. Okay, so let me actually write down the bibliography. That is quite interesting. So the first one is, log space mining. Actually, the full title is Mining in Logarithmic Space. Okay, and this is the conclusion here, right? So after you've synchronized and you've downloaded these last K blocks, what you can do is you can actually start mining on top of that. So once you have these last K blocks, you can start producing a new block right here. And from that point on, you can actually construct even a new such Nipopao given the chain that will be extended by your new block. That's the interesting observation. So this is called mining in logarithmic space. This was a paper that we wrote with my PhD advisor, Agelos Kayas. My collaborator, Nikos Leonardos, from the University of Athens. University of Athens. My advisor is now at the University of Edinburgh, and me. I did this while I was in Greece, but now my affiliation is at Stanford. And some other interesting papers are non-interactive proofs of work. Okay, work, yeah. So this describes the protocol with these superblocks and these interlinks. We actually have a slightly modified protocol for this mining in logarithmic space paper. It's fully described in there as well, and we do use a different security proof over there, which we find a little bit more elegant. This is an older paper that we have with my advisor, my PhD advisor, as well as with Andrew Miller. And then some interesting papers that are not exactly what I spoke about today, but they're very related. One of them is called Proof of Work Sidechains. And this is a paper we wrote with just me and my advisor. And what this describes is how these structures of superblocks and Nipopaus are useful in the context of interoperability, moving information from shard to shard or from chain to chain for proof of work specifically. But then we also have another paper, which we wrote later, and this is called Proof of Stake Sidechains. And this describes how to do these interoperability solutions for shards and chains that are in the proof of stake model. And this is a paper we wrote with Peter Gaggi, as well as my advisor Agelos. So yeah, these are some very interesting papers. And actually, I do have a couple of follow-up papers that we're working on that are similar to non-interactive proofs of work, and they are proofs of stake. So this is my latest work that I'm currently focusing on here at my lab, and it's something that I hope we will be able to release quite soon. It's an exciting piece of work, and it allows you to create similar constructions such as log space minting, as well as bootstrapping for proof of stake clients. That is very efficient. It's succinct, and just in the same way that non-interactive proofs of work give you succinctness. So yeah, that's all. I hope you learned something from this whiteboard session, with this short whiteboard session. And yeah, I recommend maybe that you can start, if you want to read more, you start with this paper here, the Proof of Work Sidechains paper. It's a very easy paper to read, I find. It doesn't have a lot of math. It's just about interoperability, and it makes use of these Nipopaus, but without actually going into detail about how they work internally. So it's a good starting point because it kind of uses the API of NepoPows in a manner that's a little bit black box, so it's a little bit easier to understand. And then I think at least the first half of this paper, the mining in logarithmic space, that doesn't go into the security analysis, is also quite straightforward to understand, and it explains everything that I showed in this video. Including the full construction as well as intuition about these things, why they are secure and why they are also succinct. So yeah, thank you for taking the time to watch this video. And yeah, if you have questions, feel free to reach out. Thank you very much.